All right, let's take a look at this problem. So in this problem we have, starts out by describing for us a wheel of radius r that's mounted on a frictionless horizontal axle. So that's the pulley wheel. And what we're told about this wheel is that it has some radius r. So let's label that. We know it has some radius r. And it's on a frictionless axle. Good. A massless inelastic cord is wrapped around the wheel and attached to a box of mass M that slides on an inclined surface as shown. The net work done on the box as it slides down through a distance d is given as W prime. Okay, this sounds important. So what I'm going to do just to kind of help my brain capture that information is I'm going to say, all right, I'm going to kind of picture this box sliding down through this distance d, and I know when it does so, that the network done on it, right? Notice this is on the box, that matters, is given as W prime. All right, you may assume the system starts from rest, good to know. And there is a frictional coefficient given, and that is kinetic friction. I'm just going to add a little K there to remind us that. So there is friction at this interface there, and we're given the coefficient of kinetic friction. And we're asked to determine the rotational inertia of the wheel. So cool, getting into rotation. We're going to use energy as our overall approach here, energy analysis. So just to remind us where that is, the change in mechanical energy is equal to the sum of all works done by non-conservative forces. So we need to keep our eye on the ball as far as what are our non-conservative forces here. All right, so if we're looking at energy analysis, let's just start by looking at the different states of this that we're going to study. We can say that initially I'm interested in the system when it's at rest, like right at release, right? I mean, that's kind of a nice moment because the kinetic energy is equal to 0, and all of my energy is in the form of gravitational potential energy. So that's really nice. And that will be equal to mg. Now I need to think about what will be the elevation change as the box slides down through distance d. For that, I can think about just a nice little triangle. The distance d at the hypotenuse, angle theta is the angle of incline. So what is going to be the height change? It's going to be equal to d sine theta. Okay, good. So that's my initial energy, all in the form of gravitational potential. And then finally, after I've descended through distance d, then the box is in motion and the wheel is turning. So I have kinetic energy, I have my translational kinetic energy of the box, and I have what I can call my rotational kinetic energy of the pulley wheel. So I'll need to keep track of both of those. So the box, 1/2 m v final, I'll call that squared. And then the rotational kinetic energy of the pulley wheel, which is going to be 1/2 multiplied by its moment of inertia I, which is the thing I'm after, right? Omega final squared. So that's just the equation for rotational kinetic energy, of course, where in place of mass, I have moment of inertia. In place of linear speed, I have angular speed. All right, cool. Those are the energies I have after we've descended through that distance d. And then, of course, I need to think about the works done by my non-conservative forces here. So let's think about it. Here, works done by non-conservative forces. And what we should do is pause and just do a quick free body diagram for the block, just to make sure that we're on track with what we're considering here. So we would have the force of tension to the right. We would have a normal force. We would have the weight of the block off at some theta, and then we're going to have the frictional force. The displacement would be off to the left in this case because it's going down the incline. So I've taken care of everything that's in contact with the block. It's in contact with the cord and the surface beneath it. And then I have my one invisible force, which is weight, right? So of these, you might say, well, what can do work here? What's non-conservative? So the non-conservative forces are normal, tension, and friction. Normal force is at right angles to the displacement, so it can't do any work, only tension and friction. But tension, if I'm considering this as a system, a wheel, the system being the pulley wheel and the block, tension's an internal force there. So what that means is it does the same amount of negative work on the block as it does positive work on the pulley. So since tension's internal, it doesn't contribute to the network done on the system. And this is because we're looking at it as a system. And you might want to say, well, how do I know I'm looking at it as a system? Well, back here, when we did this step, energy final, we included kinetic energies from both the box and from the wheel. So we're looking at the system as a whole. And the advantage of doing that is that tension becomes an internal force. Sometimes if you need to find the tension, if the problem is asking you for the tension, then as you've probably seen in the past, we have to split them up and look at them independently. In this case, we can say nobody's asking me for the tension, so I don't need to consider it as it's an internal force, not an external force to the system. So it doesn't do work on the system. So the work, the only non-conservative work that I need to consider here is going to be that done by friction. So friction dotted in with the displacement. That will give me here mu k that times the normal force on the block multiplied by my displacement, which is equal to d multiplied by cosine 180 degrees here. There's 180 degrees between the direction of the frictional force and the direction of the displacement. And I can see by doing some second law analysis here that normal force is going to be equal to mg cosine theta. So that's useful. And I can write my non-conservative work here as negative mu k d mg cosine theta. All right. So then I can, these three things here, I can put into an equation, right? Energy final minus energy initial is equal to the work done by my non-conservative forces. So if I were to write that all out, I'm going to start on the left-hand side of the page to give myself a little bit more space for that. Final is 1/2 mv final squared plus 1/2 I omega final squared minus initial energy mgd sine theta is equal to work done by non-conservative forces negative mu k d mg cosine theta. So there is the equation that I've rendered by doing energy analysis on the system. So you might be noticing that, well, that's probably not enough to solve for what we need to solve for here. We have too many unknowns. We have one big equation. But we're not using all the information that's given in the problem. So we're also told that the net work done on the box as it slides down through distance d is given as W prime. And maybe just really didn't want to think about that statement and how we were going to use it, but yeah, let's use that. So something that I want to go back to for use of that is the work kinetic energy theorem. So let's remember that the sum of all works, now there's no little subscript NC, right? The sum of all works on a body is equal to its change in kinetic energy. Okay? This was chapter 7. Sum of all works on a body is equal to its change in kinetic energy. And the cool thing here is that the sum of all works on the box here, the net work done as it slides down through the distance d, right, is given as W prime. So in this problem here, I can say, all right, W prime, that's my network, is equal to the change in kinetic energy. Now, this is just the box that we're talking about, right? Just the change in kinetic energy of the box. That's going to be final minus initial. So finally, the box 1/2 m v final squared. Initial kinetic energy is 0 because we're told that this whole enchilada starts from rest. So that's kind of nice here. in that what I know, what this tells me is that 1/2 m v final squared is equal to this w prime, which is given. So that's kind of, I like that because I see that I can substitute that in nicely here, right? I see a substitution right there that I can do, enter in right away, get that in terms of something I know. So that's kind of nice. That simplifies that piece there. So the other thing that you might be wanting to discuss is this omega. That might feel a little bit new to you, I don't know. But this omega here in omega final of the pulley, now you have to kind of remember how omega and V relate, right? So omega, if you think about it, the way the pulley turns, the rate at which the pulley turns, it has to relate to the rate at which the mass descends. And those are going to relate to each other through the radius of the pulley. Yeah? So think about how we can write that omega in terms of the R. So I could say here where omega final is equal to V final over R, because the radius of the pulley is given. So that's kind of nice. So that means that omega final squared, which is what the quantity that I have, is equal to V final over R squared. And kind of the nice thing about that is that I have an expression for V final. So if I take this expression with the work prime in it here, I can say that, oh, all right, I have an expression for V final squared, right? That's going to be 2 work prime, or big W, right, over M. So now that I have that, that can help me to define my omega final. So my omega final squared then is going to be equal to, see, that's V final squared over R squared. So that's 2 big W prime over M R squared. Okay, so this is right here is kind of handy because I know that this I can sub in for that omega squared. All right, so that should be pretty much all I need. I've got my expression for normal force. I have these other expressions now that I can substitute into this equation, and I should be able to substitute those in algebraically and then solve for the rotational inertia of the wheel, that I value, remembering that the m's are given in this problem, the coefficient of friction is given, and d and r are given as well.